Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh to all students. So now let's continue to part 2, chapter 2, semiconductor, where you are going to learn about built-in potential, forward bias and reverse bias. So the first keyword here is built-in potential. So what is built-in potential? Is the potential different across depletion region that creates the barrier. So if you recall last video, so we have what we call here P-N junction. So when you form your P-N junction together, so it will be three keywords. The first one is diffusion. The second one is recombination. And the third one is depletion. So what is depletion? Is depleted of carrier. So inside here there is no carrier, so you need extra energy to allow the hole to move from your P to the N type. The extra energy needed here is what we call built-in potential. So if we see here, what is built-in potential? So as I mentioned before, so we have P type here and N type here. So what is the majority carrier for your P type? Is a hole, and minority carrier is a one hole here. So hole will move from your P type to the N type, and here is your electron. Majority carrier here is electron. So we start to move from your N type to your P type. Once it go to the junction here, it start to what we call recombine. So recombine and will be vanish. So the carrier here will be vanished, and what's left here is your static carrier. So this static ion here will lead to what we call electric field. So this electric field will not allow again the hole to move from your P towards the N. So this is what will lead to the built-in potential barrier, or we call here built-in voltage. As we can see here, at your depletion region, so where is the depletion region? So this area is depletion region. So what is actually exists inside the depletion region? The carrier is already been depleted, right? So what's left here is only the charged ion. So at your N type, let's say I draw this again here. So this N, this is P. At your N type, we have a positive charge ion. At your P type, will be negative. Why here is positive? Because N type you do with group 5, right? So it's having a lot of free electrons. It's trying to donate. So we're trying to donate, you will have a positive charge here. For your P type, you have group 3, that is boron. So it's trying to accept the electron. So you have a negative charge here. So that's where the positive charge and negative charge exists inside here. Negatively charged because of you are gaining the electron. Positive charge because you are losing the electron. Okay, so let's see here how we are going to calculate the built-in potential. How you define this built-in potential is the minimum energy required to pass the barrier. Where is the barrier that I mean here is the depletion region here. Okay, so how you're going to calculate the built-in potential? So we have what we call VBI is the built-in potential, K is the Boltzmann constant, E is the magnitude of the electronic charge, T is the temperature in Kelvin, ln NA is the acceptor from your P type, and D here is your acceptor donor from your N type, and all this you can denote here. So let's say this is your thermal voltage. So what is your thermal voltage? VT equal KT over E. Okay. Okay, so for your built-in potential, if it is at the room temperature, T equal 300, so your K is 86 this is a Boltzmann constant, right? So you're going to assume the the electronic charge, is equal to 1. So how you can calculate the thermal voltage? Vt equal kT over E. What is K? 86 times 10 power minus 6. T is 300K. You denote E equal to 1. And then you can get, at the room temperature, your thermal voltage is 0.026 volt. So this will be your thermal voltage for room temperature. Okay, so let's try to do one example. It mentioned here, calculate the built-in potential barrier given the room temperature is T equal 300. Your NA is here, ND is here, and this is your NI. So how are you going to calculate? VBI equal, so because this is at room temperature, you can denote your VT equal 0.026 volt. So this is your VT 0.026 volt. Ln NA, what is your NA? 10 power of 16. ND is 10 power of 17 divided by NI is given 1.5 times 10 power of 10. Don't forget to square, and then you can get the value of your built-in potential. Okay, so what does this mean? VBI equals 0.757 volt. So what does this mean? Built-in potential is the minimum energy required to overcome or to pass the barrier, right? So let's say this is your PN junction. This is your depletion. You're going to apply external voltage. So let's say here is positive, negative, positive, negative. So you're going to apply here 0.5 volt. But it mentioned here, minimum energy required in order for the current to flow is 0.7. But here you only apply here 0.5. Do you think the electron can flow easily? No. You need minimum here. You need at least minimum here is, let's say I draw again. Let's say I apply here 0.76 volt. So it already passed the minimum energy required. So when you apply 0.76 volt, it can allow the current to flow. So it's like your turn on voltage. This is the minimum value. You need to apply more than 0.757 in order for you to have the current flow where you have free electron and free hole easily to move in the circuit. Okay, so let's go through second example. So the second example is again a silicon, and this is the temperature is not 300K. So what you're going to denote here? So you need to calculate again the value of your thermal voltage. You cannot use 0.026. 0.026 volt is only for room temperature. So in this case, you cannot use this value. So what you need to do, you need to calculate KT over E here. Okay. And then what's next is given ND, NA. This is your B, and this is your energy band gap. So step number 1, what you need to do is calculate your VT equal KT over E. KT is 86 times 10 power of minus 6 multiplied by 400K divided by 1. So you can get the value of your thermal voltage. Then after that, you just plug in the value given here. Now, NI. NI, can you use 1.5 times 10 power of 10? No, because this is not at room temperature. So you need to calculate again your NI equal, what is the formula? VT 3 over 2E minus EG divided by 2K. Okay. So replace your T here to 400K. So this is the solution. First, you need to calculate KT over E. your T here is 400, and then you can get your value of your thermal voltage is not 0.026, it's 0.034. Since it is the temperature here is 400 K, so you need to calculate again your Ni until you get the value, and then just plug into your VBI equation. So now the built-in voltage here is 0.9. So if I apply here, this is let's say your P, your N. If I apply here 1 volt, do you think the current can flow easily? Yes. If I apply here 0.5 volt, there will be no current. No current. Okay. Okay, so with that, there will be the end of this subchapter. So try to calculate again whatever you have inside the example here. And if you have any question, let me know. Yes, you can do it. Assalamualaikum warahmatullahi wabarakatuh.